Okay, please, Marco, go ahead.
Okay, great. There it is. Okay, now I got it. Okay, great. So, um, okay, so the only thing to keep in mind from last time is that we covered the fact that if you have a generalized complex structure, um, the plus and minus I eigenspaces give a pair of complex conjugate Dirac structures. And this decomposition, um, it, uh, it gives rise to basically a differential graded Lie algebra, which controls the deformation theory of this Lie algebroid L, or really of the generalized complex structure. And so, yeah, that seems to be the point, that if you want to describe a deformation of L, you would have a map from L to L bar. Okay, now, okay, so what I want to do today is introduce generalized scalar structures. And well, okay, so the definition is that a generalized Kähler structure on a manifold with a three form, with a closed three form background, is a pair, is a commuting pair. Let me call them JA and JB of generalized complex structures. And they have to satisfy a positive definite condition. So this is an open condition. And that condition is roughly, well, this is what the condition is, that if we combine them together, this may look a little strange, but if we combine them together with the inner product, we get a symmetric bilinear form, and we want this one to be positive definite. And it's a symmetric bilinear form on the generalized tangent space. This thing is what we call a generalized metric. And an alternative way of thinking about the metric we could simply view minus JA, JB. So this, now what I'm doing is I'm multiplying both by JB, because JB is orthogonal. The JB, the inner product remains the same. This generalized metric remains the same. And we get a minus just because JB squares to minus one. So this operator, minus JA, JB, we could call this G, and it contains the same information as the metric. So this G, big G, is just the inner product of G, like that. And this operator, this thing is, well, it's the product of two orthogonal transformations, so it's orthogonal. And JA and JB are both skew, and so this thing, so this thing is an orthogonal transformation it's orthogonal with respect to this this canonical metric, and it also it's also self-dual, and it also squares to plus 1, because JA and JB both square to -1. So this is just another way of viewing it, which is going to be really useful in a few minutes. Okay, so let me just give the obvious example. So if we take JA to be a symplectic form like this, and if we take JB to be the complex structure like this, and if we remember that so in a Kähler situation, we have compatibility between these structures, and so if we compute JA JB, what you'll see is that you'll get whereas if you compute JB JA, what you'll get is this. And indeed, if you look at this this compatibility, omega, so I star, or if you just look at this entry, for example, omega I, so I omega, that's basically the negative of the metric. And so this thing would be self-dual. So if I dualize this, I would get I star minus omega, right? And so this is indeed the dual of this. So you can see from the compatibility condition that this is equal to this and this is equal to this. And so a usual Kähler structure can be interpreted as a pair of GC structures which commute. And then if we take minus JA JB, so then this is going to be just the negative of this matrix. And what you see is that this would mean that we're having minus i's, which is the inverse of I, composed with omega, which is G. So what you're going to get is G inverse. So as a map from T plus T star, this operator, it just takes T to T star, and it takes T star to T exactly by the inverse transformation. And so this thing squares to plus 1. And so we get this operator which captures the generalized Kähler, which captures the Kähler metric. Okay, and we also know from Kähler geometry that the Kähler condition, which is, well, okay, actually, let me say that a little bit slower. So in Kähler geometry, we have the symplectic form, which gives, well, okay, in Kähler geometry, we start with T, Tm, and this on a 2n manifold, this has the structure group of this bundle is GL2nR. And when we choose a complex structure, this gives, when we choose a complex structure, we get a reduction of structure to GLNC. Oh, is it going to work? Oh, yeah, good. Ah, it's so frustrating. There you go. And then if you choose a symplectic form, this gives a reduction of structure to SP2NR. Okay, both of these groups are not compact, but their intersection is compact. And that is exactly the unitary group UN, which is a real group, real compact group. And it's the maximal compact subgroup of the it's the maximal compact subgroup of the groups that it's contained in. So right, and to say that it's scalar, so this is just linear algebra. All of this up to this point is linear algebra. It's about the structure of the tangent spaces. But to go beyond that, the Kähler condition, what it really is that it's saying that this reduction of structure, the fact that each tangent space has a unitary structure, or a Hermitian, the structure of a Hermitian complex vector space, that structure is invariant under parallel transport. So that if you have some Hermitian structure at one point, and then you parallel transport it via the Levi-Civita connection to another point, it will be the same structure. So this reduction is flat, is covariant constant for the Levi-Civita connection. Now, in the generalized Kähler case, okay, T plus T star of M, this has a structural group of SO2N. This is again a 2N manifold. SO2N 2N. That's SO2N 2N. If you remember what we were talking about with the Lie algebra, this actually contains GL 2NR. So it's an extended geometry. It's a the usual GL2NR is in there, is still in there, but it's been expanded out. And inside there, we have the choice of a generalized complex structure. JA is reducing, JA is reducing it now to, it's basically like you have an orthogonal, you have a metric, which gives you the SO, and then you have a complex structure, which is compatible with the metric. So you go down to the unitary group. The only difference is that this is not of positive definite signature. So just in the same way, this goes to the unitary group UNN, which is non-compact unitary group, and JB is exactly of the same type. So you could call this the A unitary subgroup and the B unitary subgroup. They will not be the same unitary subgroup. Symmetries of JA will not be symmetries of JB. But if we require them to commute, then we're going to go to the common intersection of these, which is UN cross UN. And then we've got to a compact, maximal compact subgroup of all the groups. So, and incidentally, so by the way, at this point, we could have said that because, since TM has a UN structure, it will have UN characteristic classes. It will have Chern classes. So you'll have the C2K of M inside H. Oh, sorry, CK inside H2K of MZ. And these will be characteristic numbers of this reduction of structure. Actually, I mean, we could, because it's the maximal compact, you get these Chern classes, whether you choose a complex structure, a symplectic structure, a Kähler structure, it doesn't really matter. It's the same reduction of structure. As soon as you go down one level here, you have Chern classes. So that's why people talk about Chern classes of a symplectic manifold, even though there's no complex structure in the picture. Okay, now in this case, guess what? You have two sets of Chern classes. So so this means that TM, basically this TM is going to decompose. So let's call it C plus C minus. It will decompose into two UN subbundles. That's what reduction of, when you reduce the structure to a product, that's what it means. It means that the bundle decomposes. And this bundle decomposition is into two UN subbundles, and each of those will have Chern classes. And so you're going to get CK plus and CK minus. You get two sets of Chern classes in H2K MZ. And in the Kähler case, those two sets will be equal. But in general, they will not be equal for a generalized Kähler structure. That was just an aside. But then the Kähler condition, the generalized Kähler condition, it turns out to impose, and this is something I'm not going to have time to discuss, but I just want to say it here because it's important. The generalized Kähler condition is now saying that this reduction of structure is covariant constant with respect to two natural connections which Gates Hall-Rocek called nabla plus minus, which are differing from the Levi-Civita connection by these are one forms. So H is a three form, which has three lower indices, right? The index, one of the indices gets raised by the metric, and you end up getting a one form with values in the endomorphisms. So this is a one form with values in endomorphisms of T. So that's how you convert a three form into a one form with values in endomorphism. You can add that to a connection. That connection will have torsion. This has torsion. And the way you get the torsion is, well, you know how to get the torsion of a connection. And if you look at that torsion, remember what torsion is. Torsion is a two form with values in T. And so it's what did I do? Oh yeah, so the torsion is just I don't remember if it's without the 1/2, but it's basically constructed from this, and it's usually expressed this way. So you take the torsion xy. The torsion is a vector field which depends skew-symmetrically on x and y. But if you use the metric and pair it with another vector field, then you get this trilinear operation which encapsulates the torsion. And the cool thing is that this is H, Y, Z. So H turns out to have an interpretation now as the torsion of the connection, which is important for the geometry. So it has torsion H plus or minus.
Marco?
Yeah.
So this you say these Chern classes CK plus and CK minus, these are just the usual Chern classes of the two classic complex structures?
Of the, well, they
the
are
formulation, is that right?
Yeah, they are corresponding to these two subbundles, which I'm about to discuss, and they correspond to two complex structures. Yeah,
and then this,
without even discussing that, the point is that we have a reduction. So that means that bundle decomposes as a sum, and each of the pieces has a UN structure. So it has a complex and a symplectic and a metric structure, and those will have Chern classes.
I see. And what exactly, you say the reduction of structure is covariant constant with respect to these connections?
Yeah.
What, I mean,
what does it mean exactly?
I guess you elaborate on that.
What does it mean? It means that you have these bundles, okay, which I'm about to discuss in greater detail. But the point is that we have these bundles, right? And these bundles have connections, nabla plus minus. I mean, it'll become a little bit more clear in a moment. And the point is that if you take the complex structure or the symplectic structure or the metric on this bundle, and you drag it by a parallel transport by this connection, it'll be preserved.
You're putting the plus bundle on C, the plus connection on C plus, and the minus connection on C minus.
Exactly. Okay. So it's like you have two Kähler manifolds on top of each other at the same time, simultaneously, right? This is why Rocek called these things, schizophrenic Kähler manifolds, because the bundle, the tangent bundle, kind of splits into two copies, each of which has a UN structure, but those two UN structures could be different.
Right.
This is the thing that I just remember. That's how I'm following the train of thought that I had when I was discovering these things, and I didn't really understand all of the niceties, but I understood the reduction of structure because I understood the intersections of these groups, and I could see right away that there were two Chern classes. And so I told Hitchin, there's two sets of Chern classes, and he was like, well, are they equal or something, or are they opposite to each other? Like, is it really two separate information? And I said, it seems to be completely separate, completely independent in some way. And that's when he realized that it was related to Rocek's work with I plus and I minus.
Sure.
So it was because of these two Chern classes. But anyway, no one seems to care about the Chern classes nowadays. Yes, Josh.
Yeah, no, this is really interesting because it seems a lot like what when in a paper Jeff wrote on commuting complex structures
Yeah,
on generalized Kähler manifolds.
yeah,
Talks about these like so his paper has like four different ones because of
yeah.
like two different decompositions. But I was just wondering how those match up.
It's coming. It's coming.
Oh, okay, all right,
Keep
cool.
your eyes peeled with a little what are those things? Toothpicks. Yeah.
Can I ask a question?
Yes. After that one, yes. Unlimited questions allowed.
Um, it's a. I was just wondering, like, if you just have one of the GC structures,
Yes.
uh, then you get already the two Chern classes, right?
Correct. Correct. That's what I said. That this is the maximal compact of here or of here. So if you have a reduction of structure to UNN, then to go further to its maximal compact is just a retraction. It's a homotopic. So from the point of view of homotopy theory, there's no difference between these two groups.
Okay, thanks.
You're welcome. So okay, so the generalized Kähler condition. Oh, by the way, let me go back to the definition. Yeah, I did say it. I said it correctly. They are generalized complex, and so both of these are integrable, independently integrable. That's the only integrability condition, but it turns out that integrability condition will imply this covariant constancy that I am referring to. Okay, so question, what are these C plus minus? Okay, so now we need to do a more careful study of the linear algebra on T plus T star M. So on Tm, we have let's look at it this way. So we have on this bundle this operator G, which squares. So and remember that G is minus JA JB, and G squares to plus 1. So G will have plus and minus. So we'll define C plus minus to be the plus minus 1 eigenbundle of G. So now we have T plus T star, and we have, for some reason, I usually think of them as green, but whatever. We have C plus and C minus. And okay, and let's see. So what can we say about these C plus C minus? So why did I draw them that way? So okay, first of all, let's just think practically about this. So G is minus JAJB. So if G acts on something, let's say I have a point in C plus, G will act on it by 1. That means minus JAJB acts by 1, which means that if minus JAJB on some vector is just the vector, right? That means that I can just multiply by JA, and I get that JB and JA agree on that subspace. So this is the this C plus is the agreement of JA and JB. And then on C minus, we have the disagreement, complete disagreement, where JA is minus JB on C minus. So so we could say that on C plus minus, we have JA is equal to plus or minus JB. That's one thing we can say. So that's just useful to keep in mind. I should have said even before that JA sends C plus minus to itself, just because JA and JB commute. Remember, that's the definition. JA and JB commute. So, of course, an eigenspace of JA, JB is going to be preserved by JA and JB. And that's true for JA and for JB. So these are complex subspaces for both complex structures. And so what we have is that, there's two complex structures on this vector space, but there's a decomposition of the vector space into eigenspaces for both. And so we end up with a situation where really the only data is a complex structure on C plus and a complex structure on C minus. Okay, so really there's only two pieces of data, right? There's a complex structure I plus on C plus. I plus will be, by definition, the restriction of JA to C plus, which is the same as the restriction of JB to C plus. And I minus will be also, by definition, the restriction of JA to C plus, which is minus JB applied to C minus. So we have we get a decomposition, right? And so we see that what's really going on is that we have basically just one complex structure, but then on a subspace, we're flipping the sign of the complex structure and we're building another complex structure, which of course is going to commute with the first one because it differs only by a sign on a subspace. So of course they're going to commute if you think of it that way. Okay, but the nice thing is that if we take if we take a vector, if we take a vector in C plus, right, then that means that minus JA JB of V, minus JA JB V is equal to V, which means that if we now take the inner product, this will be the same thing as VV, okay? But this is exactly the expression for big G VV. And this thing is supposed to be positive definite. So we see that anything in C plus, of course, the metric inner product will be non-zero if it's non-zero because it's a positive definite Riemannian type metric on the big bundle. But the thing is that because of the fact that the metric is a consequence of JA and JB, or because of the fact that the metric is orthogonal, it turns out that this point being positive definite with respect to the Riemannian metric means that it's also positive definite for the split signature metric. So that means that C plus is a maximal positive definite subspace of T plus T star. Okay, that's why I draw it as if it's, like the way the physicists do space, because it has a positive definite Riemannian metric on space. On time, you have a negative definite metric, and that's exactly what happens with C minus, just because there's a sign here, minus V. Similarly, C minus is maximal negative definite Okay, and then what I'm describing now makes a lot more sense with respect to this decomposition. So what you see is that all of the structure passes to this decomposition. The T plus T star decomposes into C plus C minus, and C plus is positive definite. So here you could say that. So on C plus, this metric it agrees with the positive definite metric, and on C minus, this inner product disagrees with the positive definite metric. So you end up with two Hermitian bundles. So this tells us that C plus minus are both Hermitian bundles. So they have a complex structure, I plus minus. They have a Riemannian metric, Hermitian metric, positive definite metric, which is, if you wish, plus minus of the inner product restricted to C plus minus. And they also have, and they're compatible. So we get UN structure. So we get, UN plus or minus structure group. So it really does look like two Kähler-like structures, or two Hermitian structures, okay, on two subbundles. Now, last thing is to observe that this T plus T star has a projection to Tm. Okay, we can project now everything to T. And the cool thing is that because this is negative definite, and because this is null, that means that this projection from C minus to T is an isomorphism. So this is an isomorphism, and this is an isomorphism. Okay, because C plus and C minus have the same dimension as T. Maximum null, maximum positive definite, they're all N because we're in a split signature. And these bundles C plus, C minus, they don't intersect T star. So if we project from T star, everything gets squashed together on T. So this means, so this induces isomorphisms C plus minus to T. And this implies that we get that these C plus minus is isomorphic to T, and we literally get a pair of Hermitian structures on T. And right, and the last thing to observe is that the metric, the Riemannian metric that is induced on T from C minus or from C plus is actually the same. So these two Hermitian spaces, when we identify them via the natural projection, they will give the same exact Riemannian metric, but not the same complex structures. So so let's give a more detailed description of C plus. So look at C plus. C plus or C minus, it's the same idea. We could think of this as defining a map from T to T star. So we could think of C plus as the graph of a map of bundles. It's the graph of a map, theta plus is a map from T to T star. It's an isomorphism. And any such map, I could write it as a symmetric part plus a skew symmetric part. I'm just using the fact that theta plus is in T star tensor T star. Okay, and so this means that this C plus is really the graph of a symmetric form plus a 2 form. And then if we try to do the same thing with C minus, what you'll find is that it's the graph of theta minus the same, everything's the same, but theta minus is G, same G, like I said, and with a minus B. So in the end, we obtain on the usual tangent bundle of M, now that we crowd everything, we take everything that's nicely distributed on this T plus T star, we smash it down into T where there's no room, and we obtain a whole bunch of structure on Tm. We get a Riemannian metric, 2 complex structures, and a 2 form. So we get a bi-Hermitian structure. Okay, and yeah.
Theta minus should be minus G plus B, right? Instead of G minus B.
Oh yeah, sorry, minus G plus B, sorry. I was just correcting someone else on this. Because it's supposed to be negative definite, C minus. So it should be the graph of minus G, right? If we take X plus G plus BX, that's something in the graph of G plus B, right? And if I take the inner product with Y plus G plus B Y, right, then what you'll see is that you'll only get cross terms. So you're going to get G plus B YX plus G plus B XY with a 1/2, right? And this will give me G of XY plus B of XY. So you see that if X and Y were the same, then the B part would go away and we would just get GXX, which was a positive number because G is, well, it has to be a positive number. And so that's the reason why G is positive definite. And there's no condition on B at all. So we get a Riemannian metric. We get compatible complex structures. So there's 2 complex structures compatible with the same metric, and we get a 2 form with no constraint. Okay, and this is the bi-Hermitian geometry. This is the presentation of the data. This presentation coincides with the Gates-Hull-Rocek work from 1984. That's how they described the structure, and they gave the integrability conditions on this. So, so how do you analyze integrability for this structure? Well, we already said what integrability is. Integrability is just saying that both JA and JB are integrable. And that means that the plus I eigenbundle of JA and the plus I eigenbundle of JB should be closed under the Courant bracket. Now, what's the relationship between the plus I of JA and the plus I of JB? Well, a priori, there wouldn't be any relation, but because JA and JB commute, we know that commuting operators will have common eigenspaces. So in other words, each eigenspace of the first operator will decompose as a sum of eigenspaces for the second operator, right? They play nice together. So, so this has to do with the plus minus I eigenbundles of JA and JB, which commute. Okay, and so what happens? So you end up with this situation that LA, the plus I eigenbundle of JA, this thing will split into a sum of L plus, which is a plus, and L minus. So this is LA intersect LB. That's where both JA and JB have plus I eigenvalue. This is going to be LA intersect LB bar, where they have opposite eigenvalue, but JA has eigenvalue I. Whereas on the other hand, LB is going to be, it has to be, it'll have, it'll still have LA intersect LB in it, so L plus will still be in LB. And but instead of having LA intersect LB bar, it will have the complex conjugate of that. So this will be LA bar intersect LB, so that it has the plus I for LB, but not for LA. So in total, this complexified big bundle is going to be a sum of 4 spaces, because there's 2 possibilities for the eigenvalue. So it's 2 to the 2. It's 4 possible eigenspaces. Okay, and let me just say, oh, right. And for some reason, for me, A is always red. So so this is LA. This is LA bar. And LB, usually blue. So LA, so this is LB, and this is LB bar. Okay, and these are all equidimensional. They all have the same dimension. So these all have dimension n. So in the diagram, maybe I'll draw the diagram again. So we have t plus t star. We have C plus and C minus. And notice that, okay, this may not be satisfactory on a first pass, but it is a correct argument, which is that C plus and C minus, right? They were plus minus 1 eigenspaces, so they were real. C plus and C minus are real. L plus, L minus, L plus bar, L minus bar, those are all complex subspaces. So if, and we also know that C plus and C minus are direct consequences of the L's because they're built out of the complex structures. So that means that the C pluses and the C plus and the C minus, it has to be built out of the little L's in some way, somehow. And the only option really is that you have to make them real. So you have to take L plus L plus bar, make it real, and that will be C plus. So it turns out that C plus secretly is decomposed into L plus and L plus bar. If you complexify it, so C plus complexified, this will be L plus L plus bar. You can check this by doing the following thing. You could say, suppose that J A V is equal to IV and JB V is equal to IV as well. Then what you could do is you could, so that means V is in the complexification. So that means that V and V would be in here and V bar would be in here. And so you could take the inner product of V and V bar, okay, and check what sign it has. I'm just hoping that I didn't choose my conventions wrong, but if you check this out, this will be, you can put in you can put a JA in on both sides, and you'll get sorry, what am I trying to show? I want to show this as positive definite. So right, so you could say that this is the same thing as JAV. Sorry, I'm not giving. So if I take V and V bar, we could say that this is JAV, and I'll put a minus I to get rid of that eigenspace. And here I could put JBV, and I would have to put an I. So the I and the minus I cancel out. And this is indeed G of big G of VV, which is positive definite. So anyway, you can convince yourself that what I'm saying about the decomposition is right. C minus has its own decomposition into L minus and L minus bar. So now we have a situation where T plus T star breaks up as a sum of 4 spaces in the complexification, and then you can kind of understand what these things really are. Remember that on C minus we have I minus, and the little L minus and the little L minus bar, those are just the plus and minus I eigenspaces for. These are just the plus minus I for I minus. And when we project these down, we're going to get a decomposition of the tangent bundle into plus and minus I. So I'm going to get T01 minus and T10 minus. So I'm just saying that the way you should look upon these orange subbundles is that they are the Dolbeau tangent spaces T01 and T10 for I minus, and T01 and T10 for I plus, right? But they're separated out. Instead of having them be on the same bundle, the tangent bundle, we've taken the plus Dolbeau bundles and moved them up to C plus and to this isomorphic subbundle C plus, and we've taken the other ones and moved them down. That way we separate the complex structures into like independent spaces. Okay, and there's an important lemma which I prove in the paper, in my paper, or if you want, if there's a longer proof in the thesis, but there's a short proof in the paper on generalized scalar, which is that integrability holds for JA and JB if and only if L plus and L minus are involutive. Okay, so some directions here are obvious. Like, for example, if we know that LA is closed under the Courant bracket, and if we know that LB is closed under the Courant bracket, then their intersection, namely L plus, should be integrable for the Courant bracket. And the same thing goes for L minus. So going from here to here is obvious. Going from here backwards just requires a little bit of the axioms of Courant algebroids, but it's pretty straightforward. Okay, right. So, okay, now, maybe Francis should cover at some point in his 2 lectures the flow construction, which is the main construction which we can use to produce many generalized generalized scalar metrics, many interesting ones. But I should maybe point out that so there's the examples. So here I'm going to mention an open problem. And this is something that I have worked on, but I don't have anything compelling enough to convince me to write a paper about it. But the open problem is the following. So when we look at examples of GK, okay, there's 2 things that I want to say. So from the physicist's intuition and from my experience, there's tons and tons of generalized scalar structures. There are many of them. Okay, but there's certain conditions which are totally natural that you could investigate, but where we have almost no examples at all. So let me just explain, rather than to spend time on constructing examples, I'm just going to give an overview for all the examples that we know, at least all the examples that I know. So where do the examples come from? So of certain type. Okay, so the examples, they're basically, okay, so one large source of examples is to take Kähler manifolds and you deform them. And the nicest such construction is the so-called flow construction, okay, which first appeared in a paper of Apostolov, who's here, hi Vesti, and Goduchamp, Grancharov. And it's a very interesting fact that they were even studying this at all, because they were not studying this because of Gates-Hall-Rocek, as far as I know. They were studying it because people in twistor theory have long been interested in having many complex structures which are compatible with the same metric. Can you, actually, Vesti, I don't remember ever talking to you about this, but did you ever know about the Gates-Hall-Rocek paper when you were writing your paper?
No, not at all.
Yeah, I mean, that's just an amazing mathematical, mathematical, what do they call it? Fundamental group, which really is like a non-trivial fundamental group going through twistor theory and coming back to two-dimensional sigma models. But anyway, it first appeared there in dimension, in certain dimensions for certain cases, and then Hitchin developed it a little bit more, and then I developed it more. Okay, and this is a source of many examples of deforming, and it uses, in all cases, it uses a holomorphic Poisson structure to point the way, because it is the thing that gives the deformation direction. So you need to have a Poisson Kähler manifold in order to make this construction run. And it turns out that it's an unobstructed deformation direction in the space of GK structures. It allows you to really move in a specific direction, whereby the I plus and I minus separate from each other. They initially are just the complex structure, but then they separate and they become different. Yeah, that construction, you could really spend like a few hours describing the intricacies of it. It's a pretty detailed and interesting construction. Now, okay, the next construction is cutting and gluing, which I have a few examples of, but which hasn't been. So I think that this is very promising for the open question. Okay, but I've only started this a little bit. I've only done a little bit of this work of taking GK structures on open sets and arranging so that we can glue them together. This is kind of inspired by, it's somewhat inspired by the way that you can construct Kähler toric varieties, right? Kähler toric varieties are very modular. They have different open subsets, which you can kind of glue them together to make compact examples. There's a generalization of that which can be very useful, so this is inspired by, for example, Vesti's former student Boulanger, his work on toric GK. Toric GK, they are kind of examples of the type number one, because they do admit Kähler structures, but they're constructed in a different way. They're really constructed via a combinatorial procedure, and so I would classify them as being slightly different. But this one is kind of, I don't really know where it's going to go. Third example is semi-simple Lie groups, or Lie groups, any even dimensional Lie group with a bi-invariant metric and a decomposition of the roots into plus minus subsets, and a choice of complex structure on the Cartan subalgebra. You can kind of ignore all the details. The point is that a lot of even dimensional groups have GK structures, and these are all twisted for the three form, given by this bi-invariant metric applied to the Lie bracket of x and y and z. So this is the famous Cartan three form, which generates, at least in the simple case, it generates the third cohomology of the group. But so, and the two complex structures, I plus and I minus, these are exactly a complex structure which has been left translated from the identity element all over the group to give a left invariant complex structure, whereas this one is the right invariant complex structure. So the generalized Kähler structure on these groups, so an example is S3 cross S1, SU2, SU3, and so on. These are very interesting GK structures because they're not just invariant under the action of a group. They're constructed from invariant things, but those are both left and right invariant, and so it's incorrect to think of these as being group theoretical, if you want to call them that. They don't seem to be that way. They really are geometric. And these, I studied, well, I noticed this in my thesis, but actually it was noticed long before by physicists. So the physicists studying the WZW model, they knew about this structure. Okay, so okay, now I just want to point out a few things. So here we have, oh wait, do we have any other major sources of examples? Well, okay, so here the three form is 0, or at least the cohomology class of the three form is 0. Here we can get, because it's a cutting gluing procedure, this is possible. And I think that's good. Here the three form is actually non-zero in all cases. Okay, but the real the problem is the construction of non-group examples with three form non-zero. We have plenty of examples of generalized Kähler with the three form being non-zero, being zero in cohomology, but I'm interested in finding the ones that are twisted. And so I'll formulate an open problem, which is very specific. So open problem: is there an example? Is there a generalized Kähler structure integrable with respect to a three form which is non-zero in cohomology, which A is not a Lie group, and B, I don't like that condition because saying that a space is a Lie group is kind of a weird condition, but a better condition would be that the DH cohomology is non-trivial. So what I mean by that is that this operator DH, which is D plus H wedge, this is an operator from even to odd or from odd to even de Rham forms. Okay, and this leads to a cohomology group, two cohomology groups, the H even and the H odd. These are the so-called twisted de Rham cohomology, and for this you have to kind of ignore the fact, you have to forget the fact that you think of cohomology classes as having a specific degree. just think of them as having a specific parity, but not a degree. So it could be a sum of forms that are jointly closed. But the reason we need to do this is because this wedging by h is a +3 operation. So we're doing +1 and +3. So this doesn't really make sense to think of it as a complex unless you collapse the complex into just even and odd. And for a Lie group, these are both 0. So what I would really like is to have a non-trivial 3 form with non-trivial twisted cohomology, which has a GK structure. And this is, I mean, the only, yeah. Is Vesti still here? Yeah. Does this, Vesti, what do you think about this problem? I mean, does it make sense to you?
Yes, of course. I think so. I would even add a more basic problem as well.
Yes, yes.
Just if you allow me. To know one example of a generalized scalar structure on a manifold which does not admit Keller structure.
No, but that's simple. That's already on Hopf, right?
Well, generalized scalar with H trivial, sorry.
With H trivial. So it's a very similar, it's a kind of
very similar what
opposite
you
question
asked.
in a way. Is there an example of generalized scalar manifold with H0 but non-Kähler?
Yeah.
Oh, right. Right.
It's similar in spirit. I think there is something about this cohomology that this Cartan cohomology that is.
That's right.
It's involved in this.
So yeah, I mean, but okay. So if you give me 4 minutes, I'm going to take 4 minutes, and I'm just going to.
I mean, I guess I just maybe want to clarify. I mean, you also, of course, mean. Well, I mean, you can of course deform these Lie group examples to not be strictly coming from these in like left invariant, right invariant structures, I guess. But that's
right.
Really,
but that's
not really what you mean.
Yeah, that's this. I want this. Yeah.
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 And sorry, did you say you actually there are specific examples you have in mind for class 2? I think you said this sort of toric type.
Yeah. So I have you know, I have a program, let's say, for producing examples, but I do not know if the program will work. So I have, you know, I have a program that should work if I could just get the bloody thing to work. but you know, I just haven't. So the idea is that you should be able to look in where I would look is in it's so important to mention this. Okay, I'm sorry. So I'll get back to this in a second, and this will only take me a couple of minutes to explain. So the integrability conditions in terms of the bi-Hermitian data, okay, and this is something that I'm sure all of Jeff and Mario's students have seen in great detail. It's basically that if you take the metric and you combine it with the two complex structures, you're going to get your candidate Kähler forms, but these are not closed. So these are not closed, not necessarily closed, but rather instead what happens is that they're killed by this this alternate real operator, which is sometimes called DC. And because I have two complex structures, I need to put a plus minus on this. So we have these operators, and the condition really is that DC of omega plus should be equal to minus DC minus of omega minus, and this should be equal to the 3 form. Now, remember that this is a closed 3 form, and as a consequence of this integrability, this is the key integrability condition. This is it. so remember how I said that in order to be integrable, LA and LB have to be closed in the Courant bracket. The plus I eigenbundles, they have to be closed. But I said that there's a simple calculation you can do that says that the little l plus and the little l minus, you can check that those are closed instead. And it turns out that this condition here is exactly that little l plus is involutive. And this condition here is exactly that little l minus is involutive. Okay? And because the Courant bracket involves H, that's the reason H is showing up here. It's from the involutivity, okay? So because of this fact, it turns out that DDC omega plus is equal to 0. So we have a situation where we have a class. So I have to color this in red. This is like an emergency situation where the algebraic geometers start screaming and run out of the building because their problem is that you have a class which is D closed and DC exact. And this, by the DDC lemma, tells us that it's DDC exact. And this implies that H must be 0 in cohomology. Okay, so directly, as soon as you write down the integrability condition, you see that that the complex manifolds I plus and I minus, right, cannot be algebraic because algebraic, they always satisfy DDC lemma. So that means that these examples that I'm asking for, where H, this implies that they would be non-algebraic, non-Moishezon, non-cohomologically Kähler, however you want to say it, they cannot have the homotopy type of an algebraic variety. Okay, so that means that we're in a different class, and of course it means that the complex structures on these groups, which by the way, it is a little odd that SU3 has a complex structure in the first place. I mean, when you learn about the Lie group SU3, you certainly don't learn that it's a complex manifold. It's a real group. Nevertheless, it has a complex structure. It's a complex manifold, and it's not algebraic. Okay. Yeah, I mean, it's a kind of funny thing. So that's why the program is, see, cutting and gluing, that's non-algebraic. There's no reason why you need to cut and glue. I mean, if you're using analytic subsets and you're using holomorphic maps to glue, there's no reason that algebraicity should be preserved. And so cutting and gluing is a way of constructing non-algebraic varieties, and it is something that has been used to construct a large class of non-algebraic threefolds, six manifolds. So there's a long literature from the 80s and 90s where they studied complex three manifolds, which are non-algebraic. And I think that among those, there's a possibility that some of them will be generalized Kähler. But it turns out that a lot of them that I started looking at, like the first ones that I started looking at, you eventually see that they cannot be generalized Kähler. So there's some obstruction there. And that's very worrying, because then you start to worry, then you start to wonder, am I, I mean, I'm only looking at a special class, but what if what if there's some simple reason why there never can be generalized Kähler? I don't know. I suspect not. And the reason is because the groups are there. The groups are there and they are examples. So I think it's highly unlikely that it's only the groups that will give us examples with not, which have this three form non-zero. I hope that kind of I hope that kind of makes sense. The only other thing I would say is that is that the general, so, and you should look at my, I have a short paper on the archive which explains this in detail. There's also a Hodge decomposition. So if you take this even or odd cohomology, sorry, if I take this even or odd twisted de Rham cohomology, this thing actually decomposes. This has a Z cross Z grading, just as in the Kähler case. Just as the de Rham cohomology of a Kähler manifold does. Okay, and so you can draw a Hodge diamond. Okay, and you can basically have an axis like this, where if you cut the diagram like this, this is the JA cohomology. And if you cut the diagram like this will be the JB cohomology. And basically you end up with Z cross Z decomposition of the cohomology. And you even have, and it's a Hodge theory argument. It's basically, the argument is that you have a Laplacian, you have an equality of Laplacian. So you have, you basically, you argue like this. Maybe I should just draw one more picture. So if you write the twisted exterior derivative, it actually splits as a sum of 4 operators, which I call delta plus bar, delta minus, and delta minus bar. And these are like Dalbo type operators. And there's 4 of them. And you can look at the Laplacians for each of these. So plus minus, these are all equal. And they're equal to 1/4 of the Laplacian for DH, which is basically DH star plus DH star DH. And so you end up just using the same type of argument for Kähler, and this PQ part inside the differential forms, this is defined as the IQ eigenspace for the action of J, A, and JB on the differential forms. This is not something that I had time to discuss, but if you look at that short paper, it's only a couple of pages, they'll explain how the generalized complex structures act on differential forms, and they act with eigenvalues, which are I times an integer, and then you can get a Z cross Z grading because the GC structures commute. So you basically get, you could actually think that the GC structures are defining a pair of commuting circle actions on the differential forms, and the eigenspaces, the weight spaces, give you the decomposition of the cohomology. So this is exactly kind of in correspondence with the 2,2 supersymmetry, which gives a decomposition of the 0 modes of the sigma model. And this is exactly this. So the physicists, they knew when they first were studying in 1984, when they first studied this sigma model, they knew that because of the symmetry, the 0 modes should have a Z cross Z decomposition, just because of the algebra of the supersymmetry generators. But the problem is that they kept looking at differential forms, and it was like, well, I have I plus and I have I minus. So should I take the Dalbo PQ forms for I plus? Or should I take the Dalbo forms for I minus? Or should I take their intersection or something? And the answer is that you can't really deal with I plus or I minus separately. You need to put them together into the generalized complex structure. So you need to take I plus, and you need to put it here, and you need to take I minus and put it here so that they're nicely separated out. Okay, and then you need to let this whole thing act on differential forms and then decompose. And then you get your Hodge theorem, which is what they were looking for. Okay, I'll leave it there.
Okay.
Maybe after after everyone has a go, maybe I can come back and do more later. But I'm tired now, so I'll stop.
Oh, sure. Yeah. Thanks so much for all these talks. They've been great.
You're welcome.
And can I just ask a question about, can you just go back to, I think it was like this question 3 or, the open question. I thought, aren't there there's these commuting type GK on like Kodaira surfaces, right? And like properly elliptic surfaces, like in your paper with Vesti, right? These
Yes.
and in a way surfaces as well. These all have non-vanishing H class, don't they? I think.
Wait a second.
Well, as far as you have DD bar lemma, I think.
No, but on those you do not, right? There's like these properly elliptic, like Kodaira dimension 1, right? These are not Kähler. These are, B1 is odd, right?
Yeah, but you have the bar lemma still into dimensions.
No. What do you mean?
Well, the thing is,
No.
there's one way of thinking of DD bar lemma as being a consequence of the Kähler identities, but you can make sense of the DD bar lemma without that. You could say like the way you should think of. Well, I don't remember the answer to your question. Basically, I don't remember. You're saying that there are split tangent bundle examples on,
like for instance,
on the Kodaira
like
surface.
Yeah, like I think the simplest example would just be like the unit tangent bundle over a surface of genus 2, and then take a product with another circle, and then you can put a generalized you can put split tangent bundle type GK structure
on that,
right? This is just a quotient of like H cross C, right? But these manifolds are not Kähler, and
they're not Kähler, but you're saying the GK structure has a 3 form.
Yeah, I think you can write it down explicitly. It should be let me think.
Yeah, you're right. B1 is odd. So why? Yeah. So
yeah, like the H form. Basically, will end up being like the pullback of the Kähler form on the Riemann surface direct sum, like the trivial.
Right. Okay. So what you're talking about is something which is a generalization of the Hopf surface. If you think of the Hopf surface as an S1 cross S1 bundle over CP1.
Right. Except
and
now
so
over a high
similar to that.
Right. Exactly. Yeah.
And because one of those S1 bundles is non-trivial, you're going to get a 3 form.
Yeah.
And
Exactly.
there's a tangent bundle example on the Hopf surface too, which is not the one I was thinking of.
Right.
But yeah, so there are those.
Right.
Okay, so let's add those to the list. So we have in these we have in the dimension 4 we have B1 odd 1 type GKs with H non-zero. So yeah, that's a good extra class. Yeah. So in fact, the method that I was trying to use in complex dimension 3 was somewhat like this, in the sense that you're looking at elliptic fibrations over complex surfaces, right? Where the elliptic fibration, it can have this type of twistedness, which gives rise to a 3 form. So you can find elliptic fibrations over compact complex surfaces, which are non-algebraic total space. And that's where I was looking for these.
I see.
These examples, I believe, you have only multiple fibers. So these examples are geometrizable in sense of Thurston. So these will be homogeneous spaces as well, locally homogeneous spaces.
Which examples?
That's true. Yeah. And
Which
same
Jeff
thing.
refers to. So
Oh,
these will
okay.
be elliptic vibrations, but with only multiple fibers allowed. So this
I mean,
means
they're
that
not Lie groups, but yeah.
Yeah, they're not Lie groups.
they will be, geometries in sense of
Yeah.
Thurston. So they will be some sort of.
That's true.
Oh, and by the way, when I say Lie groups, right, there are subsequent things that you can construct from these. So we also didn't have time to talk about generalized scalar reduction, but these Lie group examples, they can be reduced by certain, like for example, if you take a subgroup of the maximal torus, then it does act on these geometries, and you can sometimes do a quotient, and you can get GK structures on certain homogeneous spaces, and that hasn't been studied. So I'm just roughly putting them into the Lie group class, but there are more. Yeah, I guess the point is that it would be good to have some understanding of like the ideal thing would be something that is common in algebraic geometry. Like one of the most important and amazing theorems in algebraic geometry is the Kodaira embedding theorem. It's telling you that some complex geometry analysis thing is really an algebraic variety. And for generalized scalar structures, the typical thing to say is that, well, that goes out the window and we have nothing to replace it. But it's not so obvious. I mean, it could be that there is something that replaces it. We just don't know what that is. It's kind of similar to non-commutative geometry that in non-commutative geometry, you would like to say that your interesting non-commutative algebra can be embedded, quote unquote, into something simple. And there's a question of what that might be like. And so there isn't really an analog of the Kodaira embedding theorem for non-commutative algebra, but on the other hand, they still give generators and relations. So it's still algebraic in some way, even though they don't have a Kodaira embedding theorem. So I don't know.
That's interesting.
I really do believe that it's the kind of thing that there's a veil which separates us from like a whole bunch of stuff, and we just need to figure out the right construction to get over there. It's not there's nothing that smells like no-go theorems.
Right.
Do you think that something along the lines of Gross-Wilson construction may work? Because now we have this generalized Keller-Gibbons-Hofking construction by Jeff and Yuri. So
We have
maybe
the
one
what?
can
Which construction?
So in the Gross-Wilson construction of their paper where they prove
You're talking about the Oguri-Vafa Calabi structure.
Yeah, they prove SYZ mirror symmetry, topological mirror symmetry for Ricci flat Keller metrics on elliptic fibrations.
Oh, okay, yeah. Mm-hmm.
And the way you do this is in each of the singular fibers, you replace the metric with something which is very close to be Ricci flat.
Yes.
Is essentially is this Gibbons-Hofking ansatz modified.
Yes, so absolutely, yeah.
I wonder if using the paper by Jeff and Yuri, one can try, I mean, forgetting about the Ricci flatness, but just try to glue in these Gibbons-Hofking pieces.
What is the result in their paper again? Can you just remind me?
Yeah, what they prove is that in the large complex structure limit, the metric has a special Lagrangian fibration in a dense open setting in the manifold. I think this is what they prove, and they do this by cutting and gluing pieces of these Gibbons Hawking ansatz in a neighborhood of each singular fiber. So I wonder if you can do something like that, just forgetting about Ricci flattening. I mean, they use
when I say cutting and gluing, right, and this is not my original idea, is that you build the elliptic fibration. So basically, you build the elliptic fibration in terms of an open cover of the base, and the point is that when you glue two chunks together, what you do is you use the flow construction to glue them. So you have a Hamiltonian flow on the double overlaps in order to construct. And so there isn't really any issue about singularities of the elliptic fibration. I mean, it's not necessarily a problem that you have singular fibers, just because the entire piece has a GK structure. It's not a problem. The problem is only when you're gluing, that you need to use a certain type of gluing construction. And so what you can imagine is that you use the flow construction on double overlaps, but then on triple overlaps, the flow construction doesn't fit. And that is what brings in the three form, because you have these B field transforms. So basically the machinery is there. It should work. But the problem is that every time I try to construct one, I end up in a class which is Moishazon or something. And then it's like, you know, there's an obstruction a priori. But that's basically the idea, yeah.
Okay.
Yeah. And you know, if you think about these Lie groups, right? The Lie groups, they are kind of always of this type, right? Because if you mod out by the maximal torus, you get the flag variety. So you have this beautiful Kähler manifold, right? And it has an elliptic or maybe a higher elliptic fibration, like an abelian fibration over it. So the only examples that I know are exactly of this type. So I thought I should look for more that are just not over that are, you know, over different bases, maybe with different singular fibers. These are, I'm sorry, the examples that we know are principal elliptic fibrations. But I want one that's not a principal elliptic fibration, because I'm hoping that will, you know, that will introduce more cycles in homology, and that will give you a bigger de Rham cohomology. It will clearly show that it's not anything like a Lie group, you know. Now that I'm explaining it, I feel re-energized in this old project that's like 7 years old that I you know, never wanted to study again.
That's good.
Well, that's the point of this in some sense. So yeah, that's good.
Okay, so Francis has his work cut out for him. Is that okay? You're going to do the flow construction. What else? The Kähler potential, right?
Yes.
Yeah, so I guess I'll have to discuss symplectic groupoids as well.
Well, you know, we all have to do our dental floss and our tooth cleaning every day. So
fair enough.
Groupoids.
Yeah. Okay, well, yeah, thanks. And I guess, yeah, so that'll be next week.
Okay, thanks everyone for listening to me rattle on. See you next week. Bye.
Absolutely. Thanks, Marco. See you.
Bye.